Okay, periodic properties or trends. So put the following elements in order of decreasing atomic radius. Now before we get there, we know that going from down a group, lithium, sodium, potassium, rubidium, the atomic radius increases as we move down a group. Now it makes sense, or that's easy enough to see, because for lithium, this is 1s2, 2s1. Sodium ends with 3s1. Potassium ends in 4s1. So there's something that comes before. 5s1 for rubidium. You can see we're moving up an energy level. So as we put more electrons in, of course it should get larger. Or that's what it definitely makes sense as we go up in energy level. The problem is that when we move across a row, as we move in this direction, the atomic radius for these elements decreases, even though we keep adding electrons onto them. So that throws students off, because this has 3 electrons, this has 4 electrons, 5 electrons, and so on, up to 10 electrons. And the neon is actually the smallest of this group. It's smaller than lithium, which has 3 electrons. So what's happening is lithium is a +3 charge, has 2 electrons so it's 1s2, 2s1. And this one, what we have is the shielding from these 2 electrons. These are negative charges, and then we have a +3 charge. So we have the shielding that goes on for this guy out here, who's in a higher level. So he sees a little bit less than a +3 charge due to shielding, because these electrons are essentially in its way. It's like a spectator. He's on the outside looking in, and he's trying to see, but there's 2 people around him blocking his view. Well, if we go to neon, which is, we'll just go to the furthest point here from the other end, we have a +10 charge at the center, 2 electrons, and then on the outside we have 8 electrons. Now these 8 electrons don't affect each other because they're in the same level. They stay out of each other's way. So each individual electron is sensing the shielding of the 2 electrons, and it's seeing just slightly less than a +10 charge. What that does is it draws these electrons in closer. And again, they're all staying out of each other's way. So for neon, you have that +10 charge. You have these 2 electrons that are very close to it. And then you have these other ones that are, even though there's more electrons, they're all in the same level. They don't get in each other's way, and they get pulled in closer because of that higher effective nuclear charge. So, and I just do the one end and the other, but in between we can see as we go across the row, the nuclear charge increases, but the electrons on the outside don't see each other in the same level, and below them is the same core, 2 electrons. So all they see, each individual electron sees in the outer level, is an increasing nuclear charge, which pulls them in. So they definitely do decrease as they move across any row. So in that case, then we know that, let me draw it up here for just a real quick schematic of the periodic table. As we move down a row, we get an increase, atomic radius increase, and as we move in this direction, atomic radius increases. So, and we don't normally deal with the D or the transition elements, because they have their own rules. So we're just talking about the A groups. So if you have these, put these elements in order of decreasing atomic radius. So the atomic radius decreases in this direction, and it decreases in this direction. So if you have, let's take the periodic table. I'm going to just take these elements. You won't be able to see me do this at first, but I'm just going to circle them. We have aluminum, phosphorus, neon, helium, calcium, barium, I have phosphorus twice, sorry about that, and then chlorine. Now, anytime we move down a row, they should, well, we're going decreasing, right? So anytime we move up a row, up a column, they should increase. And as we move from left to right, they should decrease. So what will happen on the exam, I'll give you a, let me pull back a little bit here. You should be able to follow a path. You can see that we go, when we move up and over, then over, and you can follow, all you have to do, you'll do a set of ups and overs, and if it were, we wanted increasing, we go down and to the left. But you can see that since we said that they decrease going either up a column or to the right along a row, that helium should be the smallest. So once you've drawn that path, then we see that barium should be the largest, calcium should be smaller, aluminum should be smaller, phosphorus smaller still, chlorine, then neon, and then helium. Now, I could have given you every single element that is present in this path, but I just gave you part of them. So find that path, and you should be all set. Let me, okay, there we go. Now, the ionization energy, or the first ionization energy, that's where an element is, and I don't, let me make sure that how they specify this definition before I go any further. Yeah, they don't. So they're just X goes to X plus, X plus an electron. And I'm running out of ink in this pen. Hopefully I have another pen around here somewhere. There we go. So this is the first ionization energy. The second ionization energy is where the X plus goes to X2 plus an electron, and so on. But we're just going to mostly focus on the first ionization energy, the energy required to remove one electron from each of these. Now the thing is, it's only dependent on the size of the atom for that first ionization, because the thing that's going to get ionized is the electron that's furthest away. The further away that electron is, the lower the ionization energy. So you picture that the further away it is from the nucleus, the less held it is. It's that electrostatic force as the is going to be weaker as the charges get further apart. And to go to the extreme, if they were infinitely far apart, there'd be no force between them. So if they're close to the nucleus, a lot of force, which would mean a lot of energy to break them apart. If they're further from the nucleus, a weaker force, so less energy to pull them apart. So the larger the atom, the smaller and we write it as ionization energy, IE1, the first ionization energy. So it's the inverse of what we just did, which is somewhere here. And again, I put the phosphorus, but you see it's the same elements. So if we wanted to know the decreasing, for the largest ionization energy should be for the smallest element. So helium is the smallest element here, so it has the smallest atom, so helium has the largest IE1. So as helium so we want to go in the decreasing, so helium would be first, and then neon, then chlorine, phosphorus, aluminum, carbon, calcium, and barium. And say, well, how do you know that? Because it's going to be the exact opposite of this. This is going in decreasing atomic radius. So this is atomic radius, so the first ionization energy should work backwards. Since helium is the smallest, it should have the largest first ionization energy. So we can just, so the first ionization energy of helium is greater than this. So that's why I picked the same elements, just to show that they're the reverse of one another. Okay, as far as the atomic radius and the first ionization energy. Okay, compare the first, second, third, and fourth ionization energies of beryllium. Write an equation for each. So we have beryllium, and it becomes Be plus an electron. That's the first ionization energy. Be plus goes to Be plus 2 plus 1 electron, that's IE2. Be plus 2 goes to Be plus 3 plus an electron, IE3. And then Be plus 3 loses another electron, it's Be4 plus electron. So these are the first four ionization energies. And it says compare them. So I'm going to look at a table from your book. And for beryllium, the first ionization energy is 899 kilojoules per mole. That's how much energy it takes to remove the electrons from a mole worth of beryllium. 899 kilojoules per mole. Most of our chemical reactions have energies that are much less than that, maybe half of that or less, and that just shows that during a chemical reaction we don't normally jettison electrons, they just get shifted around. Then the second ionization energy is 1757. These are positive. And then the third ionization energy is 14,848 kilojoules per mole. Make sure I'm getting everybody on here. And then the last one is 21,000. Now notice we double the energy here. And then from here to here we almost go up 10 times. And then so from the first to the second we double. From the second to the third we go up almost 10 times. Then from the third to the fourth we go up less than twice. So from here to here there's this huge jump. So first thing is the ionization energies get greater as we go. That's a general trend. Once we've removed one electron, to remove another one, it means that we have to remove it from something that's already positively charged. It's going to take more energy. So each time we go up in ionization energy, we go to the next removal of an electron, it takes more energy. But there's also this huge jump here, and we can see beryllium is 1s2, 2s2. After we remove, so Be plus 1 is 1s2, 2s1. And then Be2, 1s2. And then Be3 is 1s1. And then Be4 is 1s, I guess you could say 0. There's nothing there. That's normally you wouldn't do that. But okay, but between here and here we have a jump, and that's due to we have lost the difference here. Explain why there's the jump here is due to losing all of the valence electrons. That's what's here, the valence electrons, and what we have below is the core. So once we've used up all of the valence electrons, we have to dig into the core. That requires a huge amount of energy. So the jump is due to digging into the core electrons. And then I'll explain why there's no fifth ionization energy. Beryllium only has 4 electrons. So there's no way it can have a fifth ionization energy. So every boron has a fifth ionization energy, but it doesn't have a sixth. Carbon has a sixth, but not a seventh, and so on. Okay, write the equations for the first, second, and third electron affinity for phosphorus. So phosphorus, the first one is where we add 1 electron. So we call this electron affinity 1. And then that negative ion adds another electron. It's 2. And then goes to 3. Now, we're not going to get into the trends. They try to do it in the book, but there's so many exceptions to it that it's not worth that effort. But you should know what an electron affinity is, and that it's not the opposite of ionization energy. So if we do this, where it goes to P+, that's the first ionization energy. Students try to use this as the electron affinity. That's not the EA, because it's a charged particle. What we want is a neutral atom accepting an electron, or something that's already negative accepting an electron. That would be an electron affinity, not this. So be careful of that. And then there's some, they show nitrogen has an electron affinity of 0. That just means that there's it doesn't it's not really for or against having electrons. They leave off the group 2As in the table. I wish they had put them in there because those are positive ones. They don't want electrons at all. So you'd actually have to put energy in to force them to take the electrons. So what are the general electron configuration endings for A group, for each A group? So let's just zoom out, 1A, 2A, 3A, 4A. I'm trying to make these larger. Always torn. If I make it too large, then they won't fit on the page. Make it too small, you can't see it. So this one ends, the ending is, do they use ends? Yeah, they just use NS1. So anything in any of the elements in group 1A end with either 1S1, 2S1, 3S1, 4S1. Group 2A ends with NS2. N being any number that's a row number. 3A ends with NS2, NP1. Group 4A, NS2, NP2. Group 5A, NS2, NP3. So just to show that there's a general ending. And a lot of times people will talk about these elements in that form. So that's why we're mentioning it, because you'll see it. Put this down, NS2, NP5. And then for noble gases, NS2, NP6. So if you're dealing with any of the noble gases, write out the electron configuration, they'll always end in this way, where this is either, well, it can't be, helium would just be NS2. But the rest of them would be, this would be 2S2, 2P6, that would be the ending for neon. 3S2, 3P6 would be the ending for, is it argon? Argon. 4S2, 4P6 with the ending for krypton, and so on.